Hello, my name is Julius Kiewel, and for my research, I did a project on identifying transitions with topological data analysis of noisy turbulence in plasmas. So first off, I want to start with an introduction on plasmas and turbulence. So turbulence is a pretty important problem in physics. It has to do with how energy is distributed and specifically how we can lose energy in friction and collisions, which is specifically a problem for plasmas like we have in a tokamak, which is the device we see here on the left, which is a theoretical fusion device and a very promising fusion device where we use magnetic coils to keep a magnetic field to constrain a plasma within a toroidal shape or a donut shape, which will allow us to maintain conditions which are similar to those in the sun and will allow us to create fusion like does occur in the sun. But the problem is when we have turbulence, we're going to have energy that's going in directions that we don't necessarily control, and that's going to be a problem for such systems. So therefore, we want to have some type of diagnostic that's able to tell us when these transitions occur so that we can automatically identify them, and that's the fundamental goal of this project. So the importance of topology to plasma physics is that we know that there's actually a pretty cool mathematical method called topological data analysis that essentially is going to be able to give us the number of features from a mathematical perspective inside of a grayscale image of plasma like we have in here. And we find that the number of features corresponds with the zone, zone or the type of flow that we see. So if we see something turbulent or zonal, that is to say, all of the particles or energy are moving in the same or similar directions. And this is useful, but it does actually have a pretty big problem, which is that it's very susceptible to noise. So when we look at these bottom diagrams here, these are something that is identifying the types of features that we see in the diagram in the top right. And we'll see the image on the left is the image is a graph corresponding to the image in the top right without any noise. And then the image on the right is corresponding to that top image as well, but with a little bit of noise added. And we see that these graphs look significantly different, which is going to be a problem when we want to identify those transitions as cleanly as we saw above when we're looking at real world data. So where does that put the work that I'm doing? So we're looking at conceptual models. Here we're looking specifically at when we see a breakdown, essentially when the noise covers up the features that we see. So specifically in the image to the right, we see that if we're going to be increasing the amount of Gaussian blur or the strength of a smoothing algorithm that we put onto our images on the left at the bottom, we can see that there is a point where that basically breaks down, and we see that point where it breaks down actually starts to move towards the left the more smoothing we add, even if it makes it much better as far as seeing what we want to see. So the other part of this that's coming together with that is that we want to identify the limits of noise. So specifically for this diagram, it looks very similar to the one we just saw. We're going to be increasing the radius of the feature of the circle over time, and then we're going to be adding increasing amounts of noise from a distribution. And what we see here is we see two spikes, one when the image is too small or the feature is too small within the image to be identified apart from the noise. And then the smaller spike that we see at around 70 is actually going to be when the circle breaks out. And so now the geometry is no longer a circle within a background, but it's actually just the four corners. And now we see that for that specific case, only a little bit of noise is actually enough to completely obscure those features, which is going to be a problem for identifying stuff in the future, which leads us to putting this onto real world data. So if we look at the top diagram here, we'll see that there's a turbulent, a zonal, and transitional states that we're looking at here. And when we look at the graph at the bottom, what we're doing here is we're taking those images, we're adding noise to them, and then we're blurring them by different amounts. And what we'll see is that actually they react differently to this blur, which is something that intuitively makes sense, but that also might make it easy to identify these transitions in the future, which is really what the goal of this project is about, and does give us something interesting to work with in the real world. And the next step for this project would be to continue identifying the limits of noise, running more large-scale simulations to have more plasma images within each of these regimes to train data on, essentially, and then to get real-world data if possible to see if this identification also occurs in real-world transitions. So thank you very much.